All right. So this problem I chose to do is called Fixer Upper. It's using calculus to remodel a home. So a little bit about the background is a family bought a home. The home is really disgusting. It needs to be cleaned. It needs to have some renovations done. So they hired some contractors, and the contractors aren't sure how to solve the problem. So we are going to help the contractors with the math portion. So they have to do what we say. So we better get this right so we can get it good for the family. So the first problem is the integration problem. The problem reads, when contractors were doing an inspection of the home, they discovered that the basement is leaking. They need to remove the water from the basement and reuse it in the cleaning of the home. They're trying to be eco-friendly, okay? To do this, they need to get a bucket of water up to the top of the house. As they lift the bucket, human error causes for water to spill out. The water bucket has a mass of 40 pounds. Like previously stated, it needs to be brought to the top of the house by a 25-foot rope. Every foot the bucket is lifted, it loses 0.5 pounds of water. What is the work done lifting the bucket to the top of the house? So the first thing we're going to do is we're going to have our equation. BH equals the weight of the bucket. So the weight of the bucket at its height is the initial weight and then minus the rate of weight that is lost times the distance, which is in this case is height. So we have BH equals 40, which is the weight, minus 0.5, which is the rate of weight lost as it goes up, times the distance, which is height. And then we have our domain of 0 to 25. I kind of used Mathematica throughout these problems to help me work out, even just to display it so it was easier for everyone to see. So the next step is we need to integrate the weight of change. So we have 0 to 25. So we have our 40, which is our weight, minus 0.5 times height with respect to height. So we have 40h minus 0.5, and then we're going to do our h squared divided by 2 with respect to h, and we have our 25, or 0 to 25. Okay, so we go down here and we break it down. We have 40 times 25 minus 0.5, 25 squared divided by 2, minus our 40 times 0, because we get the 0 from here, minus 0.5 is 0 squared divided by 2. We're going to work that problem out. So we get our 25 from here, our 0 from here. We have to integrate this. Okay, so then we get 843.75 minus 0. So that gives us our 843.75. So our answer for this first problem is 843.75 foot-pounds of work is needed to lift the bucket of water to the top of a 25-foot house. So we used that rope to lift it all the way to the top, and we had an 843.75 foot-pounds of work needed. So moving on to the differentiation problem. In addition to remodeling the house, the homeowners have asked us, the contractors, to fence their yards. They already have one side of the yard fenced because of their neighbors. Thankfully, they have already bought the materials for fencing. They have enough materials to fence 700 feet. Remember, one side is already fenced by the neighbor's fence building. They are asking us to figure out the dimensions of the largest area we can enclose using the materials provided. So, step 1, I drew the neighbor's building. So this is the side that's already fenced. We don't have to worry about that side. So we have these 3 sides we need to worry about. So that's the first thing I did, was draw my picture. So the maximizing area is length times width. Width plus length plus width equals 700. So that gives us 2w plus length equals 700. So we flip it around, we've got length equals 700 minus 2w. Our optimization function is a times w equals 700 minus 2w times w. So our domain for this problem is w equals 0, 350. That's because it was half, our 2W is 700, so half of that, which is W, is 350. So step 2, I punched it into Mathematica. So here's our optimization function. It output this, and then I decided to plot our function with our axis is labeled AW square feet and W feet. So as you can tell, it gave us this nice curve. Then I solved for A prime W, which gave us a critical number of 175. That's our critical number. So A double prime 175 gives us our second derivative of -4. So 175 is our local max. Then I found the area, A 175, which is 61,250. After you found the area, it's time to find the length. So we have 700 minus 2 times 175, which gives us that 350. So our answer for this problem is the dimensions of the rectangle for the largest area are 175 feet by 350 feet, giving a maximum area of 61,250 feet squared. So the largest fenced-in area we would be able to do is 61,250 feet area squared. So let's go back and look at that visually. So this area would be that 61,250 feet. And that's it.